is why we're not accepting PowerPoint in the rump session.
Some of the things appear in the wrong order. I have to, a moment. Where's my USB stick? Oh, here. Does it work?
I don't know. So please send us the slide before the session, or you can put your slide on the computer of the conference before the session starts.
I did try before the session.
And it doesn't work? Okay.
The problem is that the conference computer does not have PowerPoint, so
No.
it's...
We did.
No, you don't.
Okay.
You have WPS Office. What? What? I can. Yeah. This what? The laptop that was here before didn't have PowerPoint. No, you don't. I mean, you didn't earlier when I tried. Yeah. That's not PowerPoint. That's WPS Office. But that's not the newest version. Yeah. Yes, but it will not be correct. Yeah. Yeah, just put it there. Yeah, I know that. There I can see the time. It's my clock.
Yeah, so maybe that's the one.
Yeah, got it. Okay, my apologies for the delay. Some of the appearings of text will be in the wrong order because this is not PowerPoint on this laptop, but it should be all understandable anyway. Okay, so I'm going to talk about collapse binding quantum commitments without random oracles. And if you don't know what collapse binding commitments are, that's not a problem. I will start by motivating them and telling you why we have them. So for this, I would first like to give you an example of something we could do and which is realistic to do. So let's say we have a horse race as just a use case example, and a player wants to, so we want to construct a commitment in order to allow a player to to bet on a horse without telling the bookie beforehand what he committed to. So that's a kind of a typical teaching example for commitments. And how can we do that? Well, for example, we could take the name of the horse, Spicy Spirit in this example, and take a hash of that name together with some randomness and send this both together to the bookie. And now let's say the Spicy Spirit is the horse that wins. What does the player do? He sends the randomness to the bookie checks whether this the name of the horse together with the randomness gives the right hash, and if so, pays the money. So that's a typical approach that we might do. And now we can ask ourselves, is this a secure protocol or not? So consider a cheating player. Could the cheating player, so we are looking at the binding property now, the hiding property is not the topic of this talk. So could a cheating player achieve the following? So instead of actually sending the hash of some horse name, he just sends some fake value h that he made up in whichever way he likes, and sends this value h to the bookie. And later, when some other horse wins, say Walloping Waldo, the player performs some algorithm to find an R so that the hash of Walloping Waldo and R equals the value h he sent earlier, and the bookie sends money. So this would be a typical attack. And now I ask, is this possible? Well, if we do not specify anything about the hash function, so this is what the player wants to do, if we don't say anything, of course it could be possible. It could be that the hash function is the all zero function or something like this. But I guess everyone here, only this should have appeared. So I guess everyone here knows that in classical cryptography, all we need to do is to take a collision-resistant hash function here. Because collision resistance means that it is infeasible to find two different inputs to this function that have the same hash. And therefore, the player cannot find one input which contains Walloping Waldo and another input that contains Spicy Spirit that have the same hash. So the consequence is that H can be opened to one horse only, and not two. And now comes the big surprise. In the quantum setting, so if the adversary potentially has a quantum computer, this reasoning does not hold. So it could be that H is collision resistant, even collision resistant against quantum adversaries, but still it is possible that the player unveils to any horse he pleases. At least relative to some rather artificial oracles, such a hash function has been explicitly constructed in prior work. So the question, well, the first question you might ask is this even possible? Although this is not the topic of the paper here, I would like to tell you a word or two why it is possible in principle that this can happen, because otherwise you might stop listening because you think I'm solving a problem that can't happen. So why could it be that such an attack is possible with a collision-resistant hash function? Well, on a very high level, what could happen is that the player sends some fake value h, and this fake value h is produced with some quantum algorithm that does not compute only the value h, but also computes some quantum state psi. So it's a randomized quantum algorithm that outputs each time you run it an h and a quantum state together. So you can't just first pick the h and then compute the quantum state. They just come together. And then later, when the player knows what horse he wants, there's some other algorithm that computes from psi the randomness needed to open to that value. And now, since quantum states cannot be cloned in general, we see that there's no contradiction to the collision resistance. because this algorithm here will use up psi, we can do it only once. So we can open this hash function to whatever we want, but we cannot open it to two values at the same time. In particular, we cannot find a collision. And this has been explicitly done relative to some oracles, so it seems to be a threat that is at least possible. So the question is, also already done in this year's Asiacrypt, what do we do against this? How do we improve the commitment schemes in order to avoid what I call here the walloping Waldo attack? And there were two contributions. One was the definition of a stronger property of computational binding, because it turns out if you just use one-to-one the definition of computational binding that is used in the classical setting, even the definition does not exclude this attack. So there's an improved definition called collapse binding. I will not show you that definition for time reasons, but let me tell you that it does imply that you cannot cheat in this example that I showed you. It is nice because it composes in parallel, and it is rewinding friendly. So even in proofs that use rewinding, which are particularly tricky in the quantum setting, like when you use, for example, zero-knowledge proofs and so on, these commitments behave nicely. But the question is then, do they exist? Well, and that was the second contribution. Another notion was introduced, a security notion for hash functions, called collapsing hash functions. And it was shown that with kind of standard constructions from the classical world, a collapsing hash function implies a collapse binding commitment. So a commitment that is good for all purposes that we know. Collapsing is a strengthening of the notion of collision resistance. And well, I claim it is what we actually want from a hash function in a post-quantum setting. And it was shown that such functions exist in the random oracle model. But the big question that remained open is, do collapsing hash functions actually also exist in the standard model? Yeah. Because you could claim, well, I make up some definition and then I show the random oracle satisfies it, but perhaps it's an impossible to achieve definition. So the goal of the present paper is to show that collapsing hash functions exist in the standard model, so without random oracle. And in particular, this then also implies the existence of collapse binding commitments in the standard model. So it solves all the problems that I've mentioned so far, at least. Not all the problems in the world. So that was a bad button. Which one was it? Ah, it's back. Okay, so yeah, it appeared too much again, but never mind. So let me first tell you now what a collapsing hash function is. So I will now show you the definition. I'm showing you the definition here a bit differently than it is in the paper, because after the paper I came up with a bit more intuitive way of phrasing it, but it can be easily seen to be equivalent. So consider a hash function, and now we want to generalize the idea of being collision resistant to the quantum setting. And in the classical setting, collision resistant means we cannot find two values that have the same hash at the same time. In the quantum setting, as we have seen, this is not enough. Instead, we will ask for something which, at least on a vague intuitive level, means we cannot find a superposition of two values that have the same hash. And this is formalized as follows. So we look at an adversary that outputs a number of messages M in superposition. There should be outputs here. So here we have an adversary, he outputs a bunch of messages M. And then we take this bunch of messages, the superposition of messages, and measure which one it is, and we give that, the state after the measurement, back to the adversary. So quantum mechanics tells us that if the adversary produces a bunch of messages here and we measure them, what we give him back is not a superposition of messages, but randomly chosen one out of the messages that were in this superposition. And now this we contrast with the second game, where again the adversary produces the superposition of messages, but now instead of measuring which message he sends, we only measure the hash of the message. So we perform a measurement that takes less information about the quantum state. And that means that whatever the adversary gets back will be a superposition of several messages, or potentially a superposition of several messages that all have the same hash that we have measured, because we have narrowed the superposition down to all messages that have the same hash. And now the definition of collapsing is in principle very simple. It says that an adversary cannot tell whether he runs in this setting or whether he runs in this setting. What does this intuitively mean? Intuitively, if we ignore all the issues like computational limitations and so on, and just think information theoretically, it means that measuring M and measuring the hash of M do the same thing to the state. And doing this, and that means that the information content of measuring M and the information content of measuring hash of M is the same. In other words, measuring the hash tells you the same as measuring the message, which basically means there is no collision. This was some information theoretical argument. Of course, a hash function will have collisions. They are just hard to find. But this should be enough for now to have a vague feeling about why the definition is like it is. It's basically, the hash function is supposed to look as if it wasn't possible to send a superposition of different messages with the same hash. Okay, so that's the definition, and now the question, do they exist? And I will sketch the construction that we found on a high level. And the main tool that we use for this construction are Lawsy functions. You may have heard of Lawsy trapdoor functions. Lawsy functions is the same, except that we don't need a trapdoor, so we slightly weaken the requirements. And a Lawsy function is a function keyed by some public parameter, which can exist in two different kinds. So depending on the parameter, the function is either injective or it is highly non-injective, in the sense that the image of this function is concentrated on a rather small set of its range. And the Lawsy function definition says it is, you cannot distinguish between these two kinds of parameters. And this we will use. So the construction is this one. We take a message, and the size of these blocks here represent like how many bits the different inputs and outputs are, so that you see where it expands, where it gets smaller. So we take the message and feed it through a Lawsy function. Now the bit length of the output of a Lawsy function is considerably longer than what we put in, so it wouldn't be a good hash function. But by definition of a Lawsy function, the Lawsy function always looks injective. No matter whether we use a Lawsy parameter or an injective parameter, it will always look like it's an injective function. And an injective function is easily seen to be a collapsing function, because an injective function doesn't even have collisions. So in particular, you will not be able to have a superposition of collisions. So a Lawsy function is a collapsing function, but a collapsing function with a range that is bigger than the domain, so that's so far pointless. However, if we run the Lawsy function in the Lawsy mode, then although the range here is very big, the actual image that is used here will be a very small subset of this, so much smaller than this box hash in the end. So we have many bits, but only very few bit strings are actually possible. And now we use a universal hash function, and we can very easily show that if you apply a universal hash function to a set that is very small, then this universal hash function is with very high probability injective. So when the key here is Lawsy, then this hash function will be injective on the actual image of this Lawsy function, and therefore will be collapsing. So the concatenation of these two functions will be collapsing, and the output will actually be shorter than the message. So now we have managed to construct a collapsing function that takes a message of some length and makes a hash of shorter lengths from it. Are we done now? Well, it depends. For some purposes, that may be good enough, but generally we would like hash functions that can take a very, very long message and bring it to a short hash. While here, the more we want to compress, the stronger the assumptions about the lossy function will become. So we would actually prefer to have simple computational assumptions, as weak as possible assumptions, which means that ideally we will cut off only a few bits, or perhaps half the size, but not make like a gigabyte into a kilobyte or something. So what we need to do is to hash long messages. I need the text here. It will come soon, yeah. Okay. So how do we hash long messages? Well, in classical crypto, there are many constructions that are well known. And in particular, for our purpose, the Merkle-Damgard construction turns out to work. So if the hash function, now I get rid of these again. So if the hash function h is collapsing, but takes two blocks into one block, then a construction like this, like we hash part of the first block of the message, get something, concatenate with the second block, hash it, concatenate with the third, hash it, and so on, with some suitable padding. This is a collapsing hash function. Why is that the case? Well, what we need to show is measuring the hash is equivalent to measuring everything that goes in. And I will sketch that. So assume we measure the hash here. This, because this hash function on its own is collapsing, is indistinguishable from also measuring the inputs to that function. And now this output of this function is measured, which will be indistinguished from measuring this and those inputs, and so on. This is a bit simplified because we can't do an induction over the length because it's dynamic, etc. But the basic intuition of what's happening is captured by this. And that means that measuring the hash of the function is indistinguishable from measuring the input, and we said that is what we mean by a collapsing hash function. So I have more results, but no time, so I skip them. And I only mention my main interesting question. The main interesting question is, can we construct collapse binding commitments on even weaker assumptions? Or can we do it perhaps with one-way functions or with collision-resistant hash functions? Because lossy trapdoor functions are already a relatively powerful tool. So we would like to ideally do it with one-way functions, because classically we can do computationally binding, statistically hiding commitments even using just one-way functions. So that's an open question. Thank you for your attention.
Thank you very much for dealing with the technical issue, but still finishing on time. I'm impressed. So we have actually time for a quick question.
Classical hash functions might give you problems in the quantum world. But so can you tell me whether SHA-2 or SHA-3 have any chances of exhibiting this weird behavior?
Well, so since the random oracle on its own is collapsing, so if we assume that SHA-3 is like a random oracle or SHA-2, then we are on the safe side. Of course, it's not clear whether this is true, but basically in the classical setting, we make a similar thing. We say the compression function behaves ideally, and therefore it's also collision resistant. So I don't see any problems with those functions, especially since, for example, for SHA-2, the building block is kind of done by, I don't know, throwing the bits around heavily enough so that everything looks random. And then we build the full hash function using Merkle-Damgard, which has been shown secure here. So with SHA-3, I'm very confident that everything is fine with SHA-2. With SHA-3, we don't use the Merkle-Damgard, we use the sponge construction. There, I'm also pretty confident, but that is based on unpublished proofs that I only have on my whiteboard so far. So the sponge construction is, yeah, so one needs to additionally analyze the sponge construction, which is a bit different because it doesn't seem to be indifferentiable in the quantum model and so on. But if you trust scribbling on my whiteboard, then everything is fine there as well.
Okay, great, thanks.
All right, yeah, thanks, Dominic, for your talk.
Thank you. Yeah, you saw this, the animations came in the wrong order.
So we're using a post-quantum laptop, and it seems to have some bugs in it. That's right. The hardware is not keeping up with the ideas in the talks. Yeah.
No.
I just stand by.
I mean,
space bar.
No. Not using space bar.
Let's use the space bar. Okay. Yeah, let's just start. Let's start. Okay, so the final talk in this session about slides and laptops is by Vadim Lubashevsky from IBM, and it's on lattice signatures.
The laser stopped working.
so thank you. All right, so I'll talk about digital signatures from lattices, and sort of based on all rings. I'll explain that later as it comes along. Okay, so just a brief overview of lattice cryptography and why we use it, why we think it's, how it's sort of got started, why we started using it. So there are these two main problems, like in the worst case. So these are these problems that are sort of, for any instance, this shortest independent vector problem. So you basically find a short vector in a lattice, find a bunch of short vectors in the lattice, and then there's this bounded distance decoding problem. So these are the two main, let's say, worst case problems in lattice cryptography. And sort of the nice results were this Aitai, he found this, he kind of defined this CIS problem, which is small integer solution problem in '96, and he showed that if you can solve this average case problem, then you can actually solve SIVP. So in terms of, efficiency and stuff, this wasn't really, any good at this point, but it really got the ball rolling, and so we kind of got us to our current state, which is quite good. And in '05, Oded Regev defined the learning with errors problem and showed that it's as hard as the BDD problem in the worst case. So actually, this reduction you can sort of teach in a class. It takes 1 hour, and it's quite a simple reduction. At least the ideas are simple. This one is actually much more complicated. And the interesting thing is that from this CIS problem, you can get things like one-way functions, collision-resistant hash functions, so all the stuff that's defined in Minicrypt. Whereas from learning with errors, this is what you really need for the more advanced stuff. For example, public key encryption, FHE, identity-based encryption, and interestingly, more digital signatures are on both sides, actually more efficient digital signatures. So actually, digital signatures, you don't even need CIS. You can just use any one-way function, right? So, but that will be even less efficient. So it's like less efficient is just one-way functions, more efficient is CIS, and even more efficient is learning with errors. Okay, so I'm kind of mentioning digital signatures here because that's the topic of the talk. All right, so now what is the point of this? Why are these reductions interesting? It's because it kind of gives us some confidence that the design of CIS and LWE is good, right? So because there are some parameters such that, CIS is not, just a random problem. It's actually, if you can solve CIS for some parameters, you can solve SIVP. So we don't know exactly what parameters. So setting parameters for CIS does not come from those reductions. But at least we know that, there are some parameters that will work, and this is really what kind of keeps us working with CIS and LWE, because we know at least the design is good. If we believe that SIVP and BDD are hard, in the worst case. But, so there's a source of inefficiency for CIS. Actually, so if you haven't seen CIS before, it's basically you're given a matrix, and you try to find a vector so that the matrix times the vector is 0. And this vector should have small coefficients. So the way CIS is used is sort of used as a say a hash function or something like that. So you hash CIS, and it's hard to find a second preimage. Basically, finding a second preimage is the same as finding a collision. So the problem with CIS is that it has this random matrix, which is which defines the function, and it's big. And this was always sort of the problem with lattice cryptography for the first maybe 10, 15 years. Most lattice cryptography, not Entro was good. Is that there's a lot of storage requirements. So in terms of time, it was always fine, but these matrices were quite big. So you have to, n by m, n is 1,000, m is 2,000, and now you're going to megabytes. Okay, so what people said is, okay, let's switch to polynomials, right? So switching to polynomials, and I'll sort of, if you haven't seen this before, I'll explain it on the next slide, is actually making this matrix not completely random, but actually structured. So for example, I make this first column. The next column is going to be a rotation, some sort of function of this column. So in this case, it's a rotation with a negation on top. If you know, this is actually multiplication modulo some ring, but so we'll talk about that later. Okay, so now the nice thing about putting structure in this A is that now you need a lot less storage, and product can be computed faster as well. So the reason for this is that polynomial multiplication is basically matrix vector multiplication. So why did I write? So here's sort of an example, just a basic example. Let's say I have two polynomials, A and B. So just polynomials over the integers. Okay, so I can write that as, I just expand the coefficients times B. I'm not saying anything. So if you haven't seen this, maybe it's new, but otherwise it's kind of trivial, okay? So, so you write A times B, and then you can write it as, you know, A0 times B, A1 times BX, A2 times BX squared, etc. And you can actually write that as a matrix vector multiplication by putting your, you know, vector here. It's a row vector of the coefficients of A, and then making B, the coefficients of B go here. Then BX is just the coefficients of, you know, shifted. And then BX squared is like this, BX cubed like this. You put zeros here, and then you just, so it's a product of a vector by a matrix. Okay, so that's polynomial multiplication. Now, the thing that we were, this is over ZX. Now, if we're working over ZX mod f of x, which is we usually do when we work with polynomials, then actually this matrix doesn't, you know, doesn't have this form, but in fact it's just, you know, bx mod f is the same length as b, right? Because you just do bx and then you reduce mod f, right? So you always have the number of coefficients is the degree of f. Okay, so this is what, you know, why polynomial multiplication is the same in matrix vector multiplication. And of course, you know, this is for row vectors, but you can make it for column vectors, which is what I do later. Okay, so basically what we had before is this matrix vector multiplication is really polynomial multiplication and addition, right? So this part times this part is a multiplication, and then this part and this part is another multiplication, and then you add it together. All right, so this is what we've been working with, and so you can define the ring cis problem, for example. So that problem is given k random polynomials in some ring. Let's say we use x to the n plus 1 as our f of x, which is a popular ring to use. That doesn't matter for this talk. Finds polynomials with small coefficients so that the sum of the products is 0, right? So this is the ring cis problem, proven to be, you know, as hard, and it was proven, you know, has some hardness, right? So we showed that if you can solve cis with some, you know, over some ring, right, then you can find short vectors in any lattice that's an ideal of this ring. So the important thing to notice here is that this polynomial f kind of comes in both the problem and the sort of the hard problem that we're hoping is hard, right? So this is sort of the important part. And LWE, for example, has the same thing, right? LWE is just cis if you look at it the other way. So this is the usual LWE instance. You have the random matrix A times something plus something, and it gives you this. And you can convert it to polynomial multiplication because you don't want to have this matrix be completely random. And then you can define the same ring LWE and ring LWE problem. So here's the decision ring LWE problem is given a bunch of polynomials and AS plus EI, find S, right? So that's LWE, so it's the same thing. Given A and AS plus EI, this is error, find S. Okay, and the decision problem is basically given A and B, given these guys, A and B, decide are the BIs actually LWE outputs, or are these BIs completely random? Okay, so that's LWE. And you know, this also, we proved that, hey, if you can solve LWE for a particular f, then you can find short vectors in any ideal of this ring for the same f, right? So this is what lattice cryptography over a polynomial ring looks like. So if you can solve cis, then you can solve SVP over ZX mod f of x. If you can solve LWE, there's a quantum reduction to SVP over ZX mod f of x. So again, the important thing is that this f of x is the same in the average case problem and the worst case problem. So this kind of leads us to the natural question is, are all rings equally hard? Does it matter which f of x you put in? So there is a reduction, but does the f of x matter? I don't know, right? So there have been some results, actually recent results, this is one example of it, that show that actually you can do something for when f is x to the n plus 1, that you cannot do for regular lattices. For example, you can find, there's a polynomial time quantum algorithm for approximating the short vector with a sub-exponential, you know, not a great approximation, but a sub-exponential approximation. But sort of the result is, but the complexity of ring LWE is still unchanged, so it's a sort of a result, it's based on the underlying assumption. They're attacking the underlying assumption. As far as the average case problem, we don't know. So it's very interesting, but we're still not sure what it means. So the question is, like, is this just easier ring, this polynomial, or is it just a polynomial for which it's easier to find an attack, right? So if maybe if we think harder, or not, they think harder, you know, then maybe they will find it from any f's. They will be able to do this result for other polynomials. Maybe, I don't know, right? So we actually don't know, but you know, what would be much more preferable is if you have a scheme based on the hardness of lattice problems in every ring. So here's what I mean, and here's a result of this paper. So what we can show is that you can define an average case problem. So for example, so it's cis over the polynomial ring without modulo f of x. And if you can break that, you can actually solve the shortest vector problem over zx mod f of x for any f of x. Okay, and furthermore, this problem is actually useful because you can construct all these things here, right? So this is a bit, you know, more of what we want, because you don't really have to commit yourself to sort of knowing which worst case problem is hard. It's sort of based on every worst case problem. All right, so now I'm going to give you an amazing, so, okay, to be honest, maybe this sounds interesting, maybe I set it up okay, but this is not an amazing result. What would be an amazing result is this open problem. Is if you can get some problem, and then you can, so that's sort of do the LWE instance, right? If you can get some problem, and SVP over this would be hard for any, you know, for sort of a random instance of this problem, which doesn't depend on F, and SVP over this in these rings will be hard. And the ideals in these rings will be hard. And then from this problem, you can build all of this stuff. So of course you can do this from regular LWE, but I want it to be more efficient than LWE. So if you can solve this, that would be quite amazing, because then you would get all of this stuff based on the hardness of problems in any ring. And this is, I really sort of, you know, even more importantly than explaining to you my result, I want to sort of direct you to this problem because I think it's a really great open problem. I mean, I tried, but I have no idea. So everything I try, I can't even just not prove it, I actually can find an attack. So is this possible? Maybe. It's hard to imagine why this should be possible and this not, but on the other hand, I have no idea. So if you have, you know, if you want to work on something, I think this is quite a nice thing to try to do. Okay, so let me sort of explain this part, though, the result of this paper, and maybe explaining why, you know, this doesn't sort of naturally just carry over to this. All right, so I'm going to define this other problem over just regular polynomial rings over the ring Zx, and I call it Z less than or equal to less than n x cis D. Okay, so first of all, I'm going to define this set is, these are all polynomials in Zx with degree less than n. So that's what this notation means, okay? And so now this ZA, whatever, this new cis problem is given k random polynomials in this ring, okay? Find polynomials with small coefficients in the same ring but with smaller degree, possibly D is smaller, so that the sum of the products is 0. So it's exactly the same as the regular cis modulo sum F, except there's no reduction mod F, right? So, and now it's easy to, you can see that there is a reduction. I will show you actually now the reduction that if you can solve this problem, then you can solve the problem, the F-cis problem, right? So let's say we're given an instance of F-cis for some polynomial F, and this just consists of k polynomials. What I'm first going to do is pick random polynomials just to make sure. What I want to do is I want to, if the degree of F is small, I want to make it bigger. I want to, if these are random polynomials of small degree, I want to convert them to random polynomials of big degree. So I'm going to use these RIs to kind of fill out these polynomials. You can skip this step if you assume that D equals n equals degree of F. Okay, then I set BI equals AI plus RI times F. So I want to make these BIs the input to my new oracle that solved this problem. So these are now uniformly random here, because AIs are uniformly random in the ring mod F, and then RIs are uniformly random in something else, and then this thing is uniformly random. And then I give this guy to the solver, and he gives me some solution so that this equals 0, but not mod F, and then I just reduce mod F. And then this is 0 mod F, and if F is, has the right expansion factor or whatever, doesn't matter what it is, then it's actually going to be a solution mod F. And since the degree of zi is smaller, then these guys are non-zero. So actually, it's quite a simple reduction. You just almost take the input you're given, give it to our new oracle, and just reduce his result mod f. Now, the reason that this works, and this is the main observation why this reduction works, is that the input of f sys, the input that we get here, has nothing to do with f. Right? It's just a bunch of random polynomials of a particular degree. So it only cares about the degree of f. So it's actually not important. So just to see what, in pictures what this function is, this comparison between the old fsys function and the new one is, here is fsys, right? So for example, multiplication, sum of product of 3 polynomials, you multiply this by something, right, equals this. And here's the new one. Here's the multiplication over zx. So it basically just doubles even less, doubles the range size. So it's not as compact, maybe but it's not so bad. It's only twice as long, for example. So it's not a terrible thing. So now the question is, what can you do with this zx-sys thing? Can you base, so like, if you can solve the sys problem, you can find a small solution so this is equal 0. The previous sort of reduction shows that, then you can solve ring sys for NEF. Now, can you build something based on this? And actually, yeah, you can. So, for example, sort of the most interesting application of sys is maybe a signature scheme. Most sort of advanced thing you can build with it. Maybe there's slightly different other ones, but I think it's okay. So you can stick with signatures. So, and the construction is quite similar. So it's the same sort of Okamoto style, I would say, construction of digital signature schemes that we've had before from lattices. So the secret key is a bunch of vectors with small degree, not too small degree, and small coefficients. The public key is random vectors of a slightly larger degree in ZPX, and there's this other part, the sum of the product of these vectors t in this thing. So the important thing is, because we're using like an Okamoto style proof, is that an adversary, there exists another SI, another like S1 through SK prime, S1 prime through SK prime, that equals to T as well, with subproduct with A is equals to T. And so basically we will extract that from the adversary. So the signature looks quite similar as before. So if you're familiar with the previous lattice signatures, it's fairly similar. You just have to kind of keep track of the degrees to make sure that everything works out. So you just pick a bunch of yi's. These are your masking parameters. According to some Gaussian distribution, you compute, or if you're familiar with discrete log, it also looks the same. So you compute the hash of the sum of the products of ai, yi's. Then you set your zi's equal to yi plus csi. Then the problem with lattices, the distribution of the zi's is not, it's kind of dependent on the s. So you have to do some rejection sampling, maybe restart the procedure. Okay, and then you output the zi's basically in s. Okay, so it's not particularly, there's nothing particularly innovative here compared to the previous signature schemes. So the verification is again simple. You just check that all the norms are small and that this procedure is satisfied. Okay, so now the security proof, and this is sort of, there's one important line here, is that is the same as in Okamoto style digital signatures. Given the AIs, right, you want to solve this new sys problem, create a valid the other part of the public key, create a valid T, and now with high probability there exists another SI prime, which you don't know, but you will find it. Then you use the SIs to sign when the adversary asks you to sign, and then from the adversary signature, you can recover basically something A1 times something small plus et cetera plus AK times something small equals 0. And because the adversary does not know which SIs you used, this with high probability is a non-zero solution. So basically with high probability, this is non-zero. Yeah, okay, so yeah, so see, it kind of made an extra line, so now that's, I didn't even know what it says because it, yeah, okay, that's what I said. So with non-negative probability, the coefficients are non-zero, okay? So that's sort of the whole proof. But again, the main part, the sort of the main thing that we used is that there exist two solutions. there's S, the one we know, and the other one. So this is what I mean by Okamoto style rather than the Schnorr style signature, digital signatures where there's only one solution. Okay, so now if you set the parameters, right, so we have this better hardness assumption, but it's actually, you know, I would doubt that anyone would use this because it is, for example, for regular lattice signatures, you have public keys between 1 and 2 kilobytes, secret keys 1 kilobyte, signature size between 1 and 2 kilobytes. And for the sort of the same security parameters, you get something that's off by a factor of 10, right? So, you know, it's kind of hard to argue that in practice somebody would use something that's off by a factor of 10 to gain, you know, security that may not even be necessary, right? So what's the problem, right? Why is this so much less efficient? It's not because we don't do the mod F. That only expands it by a factor of 2. So maybe that's okay. The main problem is that these guys are not just based on ring sys, they're also based on ring LWE. So when you create the secret key, in some sense, there is a unique secret key for every public key. So you don't have this collision thing that you rely on. You actually have this indistinguishability thing you rely on, and that, I mean, I won't explain why this is better to do, but for lattices, this is the sort of the right thing to do. Okay? And this is what really results in the lower public key sizes. So if you were able to get something that makes this look random without reducing mod F, then you would actually have very comparable parameters based on hard problem in every ring. So sort of to reiterate, if you remember something from the talk, is like solve this problem, right? Figure out if there's some way, you know, to define a problem and make it as hard as sort of SVP over any ring, in lattices over any ring, and then, you know, build things on this problem. And of course, LWE, regular LWE, is one of these, is a problem, is this some problem, but we want it to be more efficient than LWE. So I think if you can do this, that would be quite a nice result, and then maybe people will say, okay, you know, you're paying a factor of 2 maybe in the size of the parameters, but now you have sort of, you don't care about which ring to use. So maybe that could be convincing. This, even I'm not convinced, but I'm definitely not convinced. And this is too much of a price to pay for not being sure. For, you know, there's really no attacks against, you know, no attacks yet that would make us want to pay this price. But really, I hope this leads to somebody, you know, getting ideas to solve this problem. You know, that would be really great. So, thank you. Yep.
Any questions?
So I wonder what is the value of this parameter k. So in your first slides, k seemed to be, no, the little k
a little
below.
K. Oh, this one. So, okay. So
it seemed to be equal to 2 in your first slides.
Yeah. So for these guys, for the thing we do, it is equal to 2 for current ones. For these guys, but that's because we're basing it on ring LWE. For ring sys, you can set it to be sort of, you know, maybe. So I think when I set these parameters, it was 5, maybe 4. But I mean, I didn't try really hard to optimize this because I knew it was going to be much worse. So k is like 5 or something. Why is k 5? Because you needed this, right? You needed there to exist more than one SI prime, so that for you know, it has to be a collapse. You know, my input, so that there's 2 possible inputs for every output, right? And if k is 2, then I would have to have my inputs be much larger. So by making more AIs, I can have smaller inputs. And this is good, better. I mean, you have to find the trade-off. I mean, why 5 and not 4? This I don't know, right? But it may be 4 or 6, right? But why 5, not 2? I can sort of tell you.
Okay, thanks. Well, there's probably more questions, but in the interest of coffee, I think we'll settle up now. So thanks, Vadim, and thanks to all the speakers in this session.
It's a unique thing, so you can just go row by row. because the first row is only a sum of a few things, right? So that when there's a collapsing, there's many possibilities, right? It's like the problem gets harder for later, for middle studies.